Hiya, and welcome to today's lecture, or this video. So today we're on week 10, congratulations. So we're going to start off with changing of variables. So one of the big things, we've kind of actually seen this so far, like we've done this a few times, especially when it comes to the normal distribution. We went from like the normal to the standard normal and stuff like that, but we're going to try to kind of see something more general. So like when we're talking about the normal distribution, the way we kind of did this was we made y. So if I have some normal distribution x, and I want to change it to the standard normal distribution, remember what we did is I took x, I subtracted the average value, and I divided by the standard deviation. And this is basically how we kind of created this. And so we're going to try to do this in a more general setting where we just have some y that's equal to f of x. And so the question becomes, well, where does this take us? So basically what we have is, remember that for a continuous distribution, so we're going to mainly look at this through a continuous viewpoint. And if we have some probability here, remember the way we do this is we take the integral from a to b, right? So these are my a and b here. And then I'm going to have some probability density function. Here I'm going to specify the little x here just so we know where that's coming from. And then we obviously have a little dx so that we can do the integral here. And so now we want to figure out, well, how does this work in terms of y? And so say we have some new distribution y where y is equal to g of x. Okay? And g here is going to be just some function. And the random variable here, y, is just going to have some density function fy of y, right? So normally we're thinking of a y b, this is equal to a to b of fy of y. So here the reason why I'm specifying this y is so that we know this function and this function are different, right? X and y change what our functions are. So this is why I'm kind of adding this little capital Y. And this actually turns out, this can be written in terms of f of x and dy dx. And so the main questions we're going to see in this section is, how do we do this? How do we go from one to another? And we're going to start this by linear functions. So what's a linear function? A linear function is going to be simple functions where we have something like, this should be an equal sign, y is equal to x minus mu divided by sigma. And so by simple functions, what I really just mean is linear functions, right? So here, if you notice, I have something times x minus some number. So I have y is equal to something times x plus some number. So this is the same thing here, right? So if you think about it, my a is equal to 1 over sigma, and my b is equal to mu minus mu over sigma. Minus mu over sigma. And so this is basically what we have. And so, okay, so like we said, we want to kind of convert this to f of x and dy. So if I take the derivative of both sides, so if I have y ax plus b, so I kind of do the naive thing and just take the derivative of both sides, what would I get? I get dy is equal to a dx. So in other words, we have dy is equal to a dx. Or another way to write this, since we want dy dx, this is just going to be equal to a. Or you can also flip it around, right? You also have that dx is equal to dy over a. So in other words, what we basically said is, okay, we know how to convert dx, right? Dx is given by this formula. And now the main question is like, okay, well, where did this f of x come from? And the f of x is really just coming from, or the f of y is coming from this formula as well. So let's kind of look at an example. This is kind of going to be a little more clear in an example, and hopefully that'll help make things make a little more sense. Actually, we'll do the example. No, yeah, we have time. Okay, so let's look at an example. So example 47.1. What we're going to start off here is with a uniform distribution. So x is some uniform distribution random variable. And the uniform distribution, this is its density function. F sub x, it's 1 everywhere from 0 to 1. and it's 0 otherwise. So you can kind of think of this as the following graph. So we have 0 everywhere. I have 0 everywhere. Between 0 and 1, I have 1. And then I have 0 everywhere else. And remember, the reason why here we have 1 is because the area has to be equal to 1. So if I were to take this area here, this is 1 times 1 is equal to 1. So that's why we have this 1 here. So this is where this density formula is coming from. And we're going to look at some arbitrary functions. So we let y be my linear function, ax plus b. And here we're going to kind of add the stipulation that we want a to be greater than 0. And we'll look at y, like what happens in the other case, shortly after. So the question then becomes, well, what is f sub y of y? So this formula here, y equals ax plus b, what this tells us is basically, like for example, if x is equal to 0, then y is equal to b, right? If x is equal to 1, then we get y is equal to a plus b. Now, why am I choosing x is equal to 0 and 1? It's because of this range here. So the uniform distribution is, or the standard uniform distribution, x has range 0, 1. That's where it's defined, right? It's 0 everywhere else. If you look at this kind of graph, it's defined from 0 to 1, and everywhere else is basically 0. So we're going to try to convert the range to y. So it turns out that y has this range. So y has range b to a plus b. Notice here, this works because a is positive, right? So since a is positive, if we're adding something to b, it's going to be going up. So in other words, what we have is y is going to be a distribution on, so y is a distribution, is a random variable with distribution on the range b a plus b. And the main thing we now want to ask is, well, what is the distribution? What kind of distribution is? So we need to figure out the density function for f of y. And since it's 0 everywhere else here, we don't really need to figure out what the density function is outside of this range, because it should just be 0 in that range. So let's kind of break this down and see what happens. So basically we have 0 outside of this range. And so let's kind of look at this. So remember how we had that dy is equal to a dx, right? So dx is equal to dy over a. Here my a is given, so we'll kind of stick with that for now. And now, so then let's look at the thing inside the integral. So we have f of x dx. So here we can convert the dx, right? Plugging this in, we get dy over a. And what is f sub x of x? Well, if I plug in, so if I what I have to do is look at this from another perspective. I want to look at this in a y perspective. So let me look at y is equal to ax plus b. And notice how if I do y minus b divided by a, this should give me my x. Oh wait, no, this is wrong. I'm doing this wrong. Rewind. So now the question becomes, well, what's my f of x, right? I'm an idiot. So what is f of x of x? So let's look up. We already have this value within our range. Within our range, this is just equal to 1, right? This is just equal to 1 inside of our range. So here, I can just say this is equal to 1 over a dy. And that basically gives us what we should have for f sub y of y. So in other words, what I have is f sub y of y is given by 1 over a if we're in this range. So if we have the range b to y, a plus b, right? So this range here is telling me where this function lives. And then we're going to have 0 everywhere else otherwise. So this is basically the idea of how we're doing these things. And so the main question becomes, well, why did we have a be greater than 0? Like, what does that actually give us? Like, who cares? Like, why can't we just say a is greater than or less than 0? So if a is less than 0, almost everything here works up until this range part, right? Because here, a plus b is now less than b, right? So we have a different range. And so what we have is the range for y is b plus a and b. Yeah, right? Because now they're flipped. So that's the only thing that kind of changes there. In terms of here, well, what changes in terms of f of y? Well, it turns out that if we were to just keep this all the same, so if I were to just write this, right? For example, 1 over a, if a plus b, this is what we'd like to write, right? Otherwise, this is going to be a problem, right? For example, a is negative. So what does that mean for my area? If I were to take the area from a plus b to b of 1 over a dy, this is just 1 over a times, or sorry, this will be the height, 1 over a times this difference. So it's a plus b of b. But like if we take any particular portion here, this range is going to be positive, right? We're going to have some positive distance here, right? This distance here is a. It's positive a, to be fair, right? Like we're trying to calculate the differences. And so what we have is, since this is going to be positive, this has to be positive as well, because we can't have negative probabilities, right? This has to be equal to 1. So in other words, we have to keep this as the absolute value, because we have to keep, yeah. Oh wait, this is the wrong way. This is b. There we go. B and a plus b, right? So the difference between these two is a distance of a, but it's the absolute value here, right? Because that's what the distance is. We're not saying the thing. It's how long this interval is, and the interval is length a, positive. And the area has to be positive, right? It has to be equal to 1. So that means this has to be the absolute value. And so this is basically how this boils down. So in other words, what we basically have is this formula. So if I have this by, so if y is equal to ax plus b, I can just take 1 over the absolute value of a, no matter if it's positive or negative, it doesn't matter. And then I can just plug in y minus b over a, right? So this y minus b, remember, is coming from this. Y minus b over a is equal to x. So it's just converting this. And this works for any distribution. And this is basically what we did for a normal distribution, right? So if I had this equation, we have a is equal to 1 over sigma, b is equal to minus mu over sigma, and we just plugged it in, right? And that basically gave us our formula. And it basically converted our phi of x. This was the, why is this under? Oh shit, this is wrong. This is 1 over 2 pi e to the minus 1/2 x squared. This is wrong. And then using this conversion is how we get this formula. So this is why we get this 1 over sigma in front, because we're generally multiplying by the 1 over a here, right? Oh, sorry, this is wrong. This is a is sigma. This is wrong too. A is sigma and b is mu. Oof. I thought I double checked these. Apparently, there's still errors in my notes. I'm gonna write these down. But yeah, 47.1 errors. But yeah, so hopefully this makes a little more sense. Your notes, hopefully, have time to edit them, so you have the up-to-date versions. But yeah, so we'll stop here because it's been 15 minutes and it's already long enough. So I will see you in the next video to kind of continue this change of variables to see where this kind of leads us. So I will see you then.